Hi, I'm Tom Schiavo, Chemistry Education Manager at PASCO Scientific, and I am here today to talk about spectroscopy. So, a spectrometer is essentially a very fancy prism or diffraction grating, and it takes light and it separates that light into its various wavelengths, and it can measure the intensity of those wavelengths, and that's where it gets interesting for us. So let me show you how we can use our introductory Amadeus spectrometer from Ocean Optics, and we can use that in a chemistry setting. So first, a little bit about how we're going to set this up. So we're going to use this through SPARKvue, and over here, when the Amadeus is plugged in, it automatically gives us these options: intensity, minus dark, absorbance, transmission, and relative irradiance. We're not going to look at all of those, we're going to look at some of them. And specifically, right now, we are going to build a graph so that we can look at intensity versus wavelength. So we're going to hit our build button. And I'm actually going to build two graphs, and I'll show you the reason why I'm doing two in a second. I'm going to do intensity versus wavelength, and we'll make that a graph. And we'll hit OK. And we get a nice XY axis graph of intensity versus wavelength, and we even get this nice background to give students a visual cue about what the wavelength means in terms of the visible spectrum. I'm going to build another graph of minus dark versus wavelength. And we'll make another graph, and we'll hit OK. And it looks pretty identical to the first graph, but there is one slight difference. The minus dark compensates for room light. So if we're studying light emitted from something, then we want to sort of compensate for the room light. So the way to do that is we need to tell the spectrometer, there's a fiber optic cable hooked up to this so the light comes in here. We need to tell it that visible light is coming in and we're subtracting for that, and we also need to tell it how long to look at the visible light. So it's almost like setting an aperture setting on a camera. So we're going to configure our sensor, edit the spectrometer properties, and for this particular portion of the experiment, I'm going to make the integration time 300 milliseconds. And I want to subtract the visible light, so I'm going to do a save dark. I'm going to hit save dark. And OK. And we are done. So we're all set up, and I'm just going to hit start so we can see a key difference here. So here's my intensity versus wavelength, and I'm going to hit start. And looks nice, 0 intensity, and over here looks nice, also 0 intensity for the minus dark. But if we look a little closer, and this is what the SPARKvue software allows us to do very easily, if we look a little closer, it's actually not quite 0, and it's picking up some specific lines, whereas the minus dark, if we look a little closer, is much closer to 0. Still, there are some noise in there, but it's not as obvious as it is over here. And that gets important depending on when we're looking at spectral lines. We want to try to just look at the spectral lines of the sample. So we're going to rescale this to an appropriate setting, and we'll look at some samples and see what's happening. So that looks good. We'll rescale this one just for the heck of it. And first, I'm going to look at a toy and see what's happening. So I have a little battery-powered blinking LED light, and it's giving off red, yellow, blue. So we'll see what's happening. We'll look at each of those individually. So if I look at the yellow light, I put that up to the fiber optics, then I get this nice peak at yellow. That makes sense. If I look at the red, I get this nice peak in the red part of the spectrum. And if I look at the blue, I get this nice peak in the blue part of the spectrum. Make sure you hold that on there. Good. There we go. So now we can look at a sample you would look at in a chemistry class. So I have helium in here, and I'm going to line this up. And this is where the ring stand and the clamp are very useful. I can get those to line up. I don't have to try to hold it steady or anything. And I'm just going to turn this on. and try to line it up so that we get nice peaks. And that's pretty good right there. So we're getting some peaks. So this is where it ties into chemistry, where we can talk about the different wavelengths of light given off, correspond to different energies of light, which then correspond to different electron transitions within the atom, you know, ultimately leading to the Bohr model and quantum mechanics after that. But here's something that the Amadeus allows us to do that a typical classroom spectrometer doesn't allow us to do. We can take this, and instead of just saying, oh, there's a red and there's a yellow line, we can actually look at the wavelengths of those things. So I'm going to hit stop so I can collect my data. I'm going to turn this off. And I'm actually going to look at the minus dark because I'm going to zoom in a little bit. So there's a couple of big peaks that we definitely notice, but there are probably some other littler peaks that we don't notice right away. And if you zoom in on this, then you notice these other littler peaks that weren't as obvious when you were scaled out. So it gives you a good chance to look a little closer at the data. And when you want to look at the data, this is again where SPARKvue software comes in. So I'm going to look at this biggest peak for helium, and I'm going to do some analysis. Click on my palette and identify a particular point right there. And this tells me that the most intense peak for helium is at 588 nanometers. And this is one of the ways that helium was identified as an element before it was actually isolated, because the sun gave off a spectral line here that wasn't known to any other known samples at the time. Right, good. So we can look at a emission spectra fairly easily, and we can do some analysis of those wavelengths. For chemistry, we also want to look at solutions. And so we have a couple of colored solutions. And we're going to look at why these are colored and what they're doing in terms of their wavelengths, and the intensity, and then we'll also get into absorbance and transmittance. So I'm going to build a new page. And again, we'll go intensity versus wavelength, just to give us a nice clean graph. Well, we'll have to delete our old runs. That's another thing that Spark allows us to do. We can save the runs, or we can hide them or delete them. I just want to get rid of that. And I'm also going to build a page of absorbance versus wavelength in a graph. And finally, transmission versus wavelength all in the same graph. And this will give me a nice way to compare those two things. Okay, so I have my intensity, and I have my absorbance and transmission. And now we need to reconfigure the Amadeus a little bit so that it can hold the samples. So now we're going to shine a light through samples instead of looking at a sample of colored light. So I'm going to attach my fiber optic cable here. And this is a little light source that can be plugged in. And now there is a light in there that will shine through the sample, and we'll be able to do some spectroscopic measurements. So I'm going to, again, we have to do a little bit of configuring to tell it what to do. I'm going to go back here, and I'm going to configure my sensors. And this time, edit my spectrometer. I'm going to change this to 150. And hit OK. In order to get smoother sampling for solutions, we're not looking for peaks, we're looking for sort of smoother curves. Typically, you can average multiple runs so that those runs get all averaged together and you get a smoother curve. And you can average what are essentially the pixels together to give you a smoother sample. You get a little less noise. So I'm going to average these. I'm going to average 4 samples. And I'm going to boxcar this. This is how we smooth things. I'm just going to pick 7. And so that's good for the time. And now we need to, again, tell the spectrometer what's light and what's dark. So I'm going to save a dark reference first. So I'm going to unplug the light, so now there's no light in there. And I'm going to put this black plastic cuvette, piece of plastic in there, so that no light is getting through to the detector. And I will save the dark. And now these are water solutions. So I'm going to put a water sample in here. And I'm going to save the light reference. And I'm going to hit OK. And done. OK. And I'm actually going to start with the water in here just to see what's happening. And we get a broad spectrum, not a line spectrum like helium, because this is actually the spectrum of the light bulb that is used in the light source. So now, if I look at my samples, I can see what's happening with these. So this is a green sample. And if I put this in here, it looks like there's lots of red intensity. There's a dip in that sort of red-orange area, and then there's some more green. And that's primarily what we're seeing, is the green. And if I put the red sample in here, now again, the shape of that curve changed, and now it's absorbing all of the sort of purple, blue, green, and it's letting through lots of red. Now the other way we can look at this is with our intensity and transmission. So if I go to this next page, I'm going to zoom in on the visible spectrum parts of this. So I'm going to just look at 400 or so nanometers over to 700 nanometers. And same thing here. I'm going to look at, this is percent transmission, so I'm going to actually scale this also. You shouldn't have more than 100% transmission. So we'll rescale that to 100. And we will bring this over to the visible spectrum and sort of stretch that out. And again, we have a little bit of noise going on in here, but we'll still be able to get the effect of the absorbance and transmission relationship. I'm going to scale this a little bit also, because normally you don't get absorbances greater than 3. So we'll go to 5 or so. OK, so now if I put my green one in there, I have to scale this a little bit more so we can see it. The green one is absorbing lots of, these aren't scaled perfectly, there we go, let's move this over, there we go, now I can see it really good. It's absorbing lots of red, that's why it's appearing green, and it's transmitting lots of green, that's why it's appearing green. Right? So there's a relationship between these two things, and if you have them lined up nice, then you can actually see this relationship. And we can go back to our intensity graphs just to see what's going on. For the red, so on the red, I'm getting a little bit of noise in this part of the spectrum, but we'll see what's happening over here. It is absorbing lots of this blue-green, not absorbing any of the red. That's why it appears red. And over here, it is transmitting lots of the red and not transmitting lots of the blue-green. So we have this inverse relationship between these two things. Right. So we can use our spectrometer as a way to study emission spectrum and relate that to structures of atoms. And we can also look at solutions and measure, why, sort of the relationship between light and matter. Why does this appear the color that it appears? And the spectrometer allows us to do that and allows us to quantify that information. Thank you very much. This has been a PASCO video. If you have any questions, feel free to reach me at chemistry@pasco.com. Thank you.